Alright, this is probably the video you guys have been waiting for. Problem number 51, chapter 4. Um, I'm just glad I didn't have to make this video twice. I saw that the other ones were having problems before I made this one, so that's always good. So let's go ahead and get started. It will be a long video because this one has a lot of algebraic steps, and to be honest with you, I like this problem a lot because you know very little, that you're given very little in the problem, and you're able to find the coefficient even with a lack of values. So we're going to start. Actually, I'm going to draw the ramp on this one just so everybody's on the same page. You don't have to draw this. Obviously, you could go straight to a free body diagram. So if a object on a ramp, I'm going to say you have positive. Actually, I should rewrite that. This is positive in the x direction. This will be positive in the y direction. And I'm actually going to make a list of things that we know. Okay, and this list is important because you need to have a clear definition of the terms. So I'm even going to do that before I do the free body diagram. So we're going to say we don't know the mass. So m equals question mark. I'm not going to box it because I'm not looking for it, but I just don't know it. I know theta. I don't know. Well, actually, I can say it would be initial will be 0 meters per second. But I was going to say we don't know the final velocity, so we can write that as a question mark. We also don't know the final velocity if we're dealing with friction, so I'm going to call that V1F. Okay, again, V1F is final velocity with friction. We don't know the value, but we do know it equals 1/2 of the final velocity without friction. And we don't know the acceleration without friction. And we don't know the acceleration with friction. So I'm using F to mean it has friction, and without the F, it's just without friction. Okay? So those are the variables I know. Now let's go ahead and do a free body diagram. I'm going to have a dot here, and the force of gravity is going to go straight down. And I could express that that's the same as m times g. There we go. And I'm going to have a normal force that's perpendicular to that ramp. Do my best to make it look perpendicular to that ramp. That looks pretty good right there. And if it's sliding down the ramp, I believe that was the case. Let me double check that. 51. Oh, it's a child sliding down a slide. I forgot it's not a ramp, it's a slide. And it's the same idea though. So we are going to have friction then going up the ramp, and you should have the frictional force and the normal force perpendicular to themselves, just to be clear. So you can see there's a right angle here. You wouldn't necessarily draw that. I'm just showing you that. That's how I. Oops. Have to do that again. There you go. And then we have to figure out the component here. So again, you use a dotted line for the components because they're not actually there. So this angle here is equal to theta. Just basically, what do you call it? Similar triangles. So you wouldn't have to, shouldn't have to think too hard about that. If you do have trouble with it, though, I suppose I can show you that. If you draw force of gravity going straight down like this, okay, and you know the normal force goes perpendicular like that, so that's perpendicular, then this line would go straight down, okay? Then if you connect this line would be parallel. Let me change that to green. This line in green right here is parallel to the ramp, which means you have to have a perpendicular line right here. I'm sorry, perpendicular angle right there. So I don't know why it's a perpendicular line. Perpendicular angle, this one's perpendicular. So whatever this is right here, okay, this angle in this blue area I'm marking here, well, that plus 90 would equal this space. Well, if this is 90, let's make this smaller. And no, I already had that color. Let's do, we can do this. If this is 90 here, and then we know that we have a 90-degree angle here, the light blue, this, or cyan, plus 90 would have to equal this angle here. So the angle would have to be the same. Here. This would have to be the same as the angle right here. Okay, so you're just dealing with similar triangles. You do not have to label everything I just shown you. I'm just making sure you can understand why that would have to be the same angle. You should get to the point where you just memorize that it's the same, and then you would just do that and label it. Okay, so I'm going to go ahead and take that off so we can read what we're working on. So basically we have the sum of the forces, I'm sorry, not sum of the forces, the force of gravity in the x direction here, and the force of gravity in the y direction there. We can even rewrite that in an equation. We're going to have the sum of the force, why do I keep saying sum? Oh, no, I guess we could say that. Oops. Some of the forces actually would be okay to say, because if we're talking about frictionless, then some of the forces in the x direction would actually equal Fg sine of theta if we're saying without friction. Okay, and then the sum of the forces in the y direction would equal mg sine of theta no wait, not sine of theta, what am I thinking? Cosine. Let's do that one later actually. Oh, no, fine, we'll do it now and I'll just reference it to it later. Let's do normal force. So we'll do normal force minus Fg cosine of theta. Okay, but I think we're going to have to do a color coding on this one. So this color will mean we're talking only frictionless. Okay, if it's not, and we'll think of a color for friction later, but so this one, that's frictionless. Okay, so this is frictionless and this is frictionless. So let's go ahead and what else will we analyze here? If we were dealing with the sum of the forces here, we could say that A equals the sum of the forces in the x direction divided by the mass. This is A being the acceleration without friction. Well, if we used this equation with the other equation towards the top, we could explain that the mass times the acceleration without friction would equal Fg sine of theta. We can obviously write Fg for mg, so we can say m times A equals m times g sine of theta. Go ahead and cross off the mass, and now we have that the acceleration without friction will be g sine of theta. So I'm going to highlight that with our frictionless values. And we don't actually have any values for the acceleration, right? We marked that before. So we're going to have to redefine these forces and the acceleration in terms of the velocity, basically. Let's do it with purple here. This right here is the key to the whole problem. So I'm actually going to make it a lighter color because that's actually showing a little bit difficulty reading that. Let's try this color. There you go. So that's the key to this problem. Without that relationship, it would not be possible. So let's think about the velocity. We need an equation that uses velocity and acceleration, but doesn't use time, because we have no use of time here, and either forces the equation. So we are going to have to use the third equation from kinematics, the only equation that doesn't use time from kinematics. So we can go ahead and write V1 squared equals V initial squared plus 2a times x minus x initial. Now we don't know the positions, that's okay, we'll just go with what we do know. We do know that the initial velocity is 0, so that's going to go away. And we can go ahead and plug in, yeah, let's go ahead and show you that. Oh, wrong color. This a here, we're going to substitute out with the equation we just did earlier. So we're going to go ahead and write it as V1 equals the square root of g, 2g, sorry, I forgot about that, 2g sine theta times x minus x initial. Okay, so this is another equation that's just talking about a scenario without friction. And at this point, it might be a good idea to go back to our understanding here. So we're going to go ahead and see, can we form the sum of the forces in the y? Because if we're going to be talking about friction, we're going to be able to define the normal force. So let's go ahead and we know that the sum of the forces in the y should be 0. Should have had that before. So we have Fn is going to equal Fg cosine theta. So Fn will equal mg cosine of theta. And that would be true regardless of friction or not. So we're just going to say yellow here is true for friction and without friction. Okay, so let's go ahead and see if we can explain the sum of the forces in the x direction now with friction. So we're going to have the sum of the forces and the x direction with friction. So I'm going to put an F there after the x will equal mg sine of theta. Remember, that's just the force of gravity, the component of the force of gravity that's in the x direction, minus the coefficient of kinetic friction times the normal force, because that's just another way of saying force of friction. You could rewrite coefficient of kinetic friction equals FFR divided by Fn. If you just multiply Fn over, then this is the same thing. And that's going to equal the mass times the acceleration with friction. So this equation, I guess we'll do, this teal color tends to turn out nice. This equation is dealing with friction. This equation was necessary in order to get this part. So going forward, we need to be able to explain the acceleration with friction. So let's go ahead and isolate for that. So we would have, the acceleration with friction equals mg sine of theta. Oh, and, sorry, I just saw this. We can plug in this for Fn. So we're going to write Fn minus the coefficient of kinetic friction times m times g cosine of theta, and all of that would be divided by the mass. So just to make sure you guys see everything I'm doing, I just divided everything by this mass that I'm highlighting next to the AF. So that is here now. So I could isolate for AF. That makes the masses cancel out, which is nice. And I can factor out the G. So you would have the acceleration with friction would equal G times the sine of theta minus the coefficient of kinetic friction times the cosine of theta. So we said friction would be the teal color. So this is the, whoops, should have been bigger. So that's the acceleration friction, I'm sorry, that's the acceleration with friction in mind. So if we're going to be able to use these accelerations, we're going to have to figure out a way to combine the two equations with friction and without friction using the kinematics equations. If we relate back to the velocity equation, the third equation from kinematics, we will have V1 final equals V1 final with friction squared equals V initial with friction squared plus 2 times the acceleration with friction and then the position change. And we're actually going to take the equation we just solved for. So all of this, oh, that's too big. All of this goes there. So right here. And the initial velocity squared is 0. So we'll have to do V1 or V final with friction equals the square root of 2g sine of theta minus the coefficient of kinetic friction times the cosine of theta times the position change, so displacement. And that explains our velocity in terms of the velocity with friction. Okay, I'm going to have to zoom out because we're going to have to take a look at what we've gotten so far. Alright, pretty good amount there. So just a reminder, the teal is an explanation of the velocity and acceleration without friction, and the cyan here is going to be our values with friction. So technically this is an example of friction as well. So we need to combine them with that. I'm going to have to erase that again. That doesn't look very good. Come on, let me take it out. Didn't work. That's fine. Let's just do this. So friction without friction, and this is the key. So what we need to do is take this equation and this equation, plug that in here, plug this in there. It's going to be long, okay? I might even need to zoom out more. Okay, let's try this. So you have, well, yeah, I'll just do it this way. Square root of 2g sine theta minus the coefficient of kinetic friction times the cosine of theta. And then you have the final position minus the initial position. Okay. That's the problem. When I zoom out, I write bigger. Okay, I'm going to erase this and do it again. We're going to have to zoom in, write it in pieces, and then zoom back out. That's weird. Why did it disappear? Okay, so let's do this again. 2g sine of theta minus the coefficient of kinetic friction times the cosine of theta, and then the change in position. Then that's going to equal 1/2 the square root of 2g sine theta, and then the change in position. Okay, so that's the combination of those equations. Now I can zoom out so you guys can see it all. Now, it's obvious that we're going to have to square everything. Okay, so we're going to have to square all of these values. And we're going to have to square all of those values. So you're squaring that 1/2. So you're going to have 2g sine of theta minus the coefficient of kinetic friction times the cosine of theta times the displacement equals 1/2 squared is 1/4 times 2g sine theta, and then times the displacement. Okay, now this is where it gets cool. At least to me, I think this is cool. You have several things you can cancel out. We can divide by 2g. Wait, is that a color I already used? I haven't used orange yet. Let's do that. So we can divide by 2g from here and here. We can divide by the displacement. So those go away. So let's go ahead and do that first and clean it up a bit. So just dividing all of those, so you have sine of theta minus the coefficient of kinetic friction times the cosine of theta equals 1/4 the sine of theta. That already looks pretty manageable. So now I'm just going to subtract. I'm going to zoom in. I'm going to subtract the sine of theta from the left over to the right. So you're going to have the negative coefficient of kinetic friction times the cosine of theta equals, again, you're doing 1/4 the sine of theta minus 1 sine of theta, so that's 4/4. So you can say a negative 3/4 sine of theta. Now we can divide by negative cosine of theta. So you have the coefficient of kinetic friction equals a positive 3/4 the tangent of theta. And look at that. We have theta, so we can figure out that value. You have the coefficient of kinetic friction will be 3/4 the tangent of 28 degrees. Oh, that video took a long time. So we have 3/4 the tangent of 28 degrees would be 0.3987. With significant figures, you have the coefficient of kinetic friction is 0.40. And that's your answer. Long problem. I was hoping I'd be able to finish it before the battery symbol came out, but I am not redoing it for that. So, again, lots of algebra on this. You are only given an angle and the relationship between the velocities. Keep this in mind. You guys could have done this series of equations. The only thing that would have been different would have been the ratio between the final velocities. But when you're doing the Atwood lab, if you knew, if you measured, for example, the velocity with the frictional value from the ramp, and then you were able to figure out what the velocity should have been based just on the force involved, you could have done it this way, and the only thing you would have needed to measure was the angle of the ramp, and everything else would have fallen into place. So um, it's a example of your homework can help you with your labs and simplify them. Now, I didn't expect you guys to do it that way, but if you could have, and it would have been impressive if you had. So um, I really like this problem because it shows you that although you're not given much information, you now have the tools to do some pretty complex calculations.